All right, welcome back to another episode of Science with Surbeck. Today what we're going to be talking about is reaction mechanisms and catalysts. Now, a couple of objectives that I want you to be able to meet by the end of this video are as follows. Objective number 1, explain what is meant by the mechanism of a reaction using the terms elementary steps, rate determining steps, and intermediate. Objective number 2, derive the rate law for a reaction that has a rate determining step given the elementary steps and their relative speeds, or conversely choose the plausible mechanism of a reaction given the rate law. Objective number 3, describe the effect of a catalyst on the energy requirements for a reaction. Objective number 4, relate the factors that are important in determining the activity of a heterogeneous catalyst. And objective number 5, explain how enzymes act as biological catalysts using the lock and key model. So we start out here with reaction mechanisms. And reaction mechanisms are defined as the process by which the reaction occurs. So specifically, what a reaction mechanism is doing is it's describing the order in which bonds are broken and formed during the course of a reaction. Now, what these reaction mechanisms are going to do is it's going to provide the detailed steps that occur at the molecular level as the reactants are turned into products. Okay, so to get the idea or understand the idea of these steps, we go over this topic that is known as elementary reactions to be able to understand these specific steps. So elementary reactions are defined as any processes that occur in a single molecular step. So basically what we're saying here with elementary reactions is this is breaking down each and every little step that occurs for those reactants to become products. Now, these elementary reactions have the following characteristics. 1, they each have a rate constant. They also have their own activation energy as well as their own rate law. And then that they're also classified by their molecularity. Now, I want to take a deeper look into this term known as molecularity. Molecularity is defined as the number of molecules present in an elementary step or in a single molecular event. Now, there's 3 common types of molecularities that we'll talk about in this class. The first type is unimolecular, and these are reactions that involve one molecule. We also have bimolecular, and these are reactions that involve the collision of 2 molecules. And then our other molecularity that we'll talk about is a termolecular step. And these are reactions that involve simultaneously collision of 3 molecules. Now, like I said above, each of these elementary steps are going to be classified by their molecularity, and they had these 4 characteristics that we discussed earlier. What I want to do now is I want to relate those characteristics to each of the molecularities that we will discuss. So we can tie together now the concept of rate laws and that business of elementary steps. So remember this, the rate laws of the elementary steps determine the overall rate law of the reaction. Now, it's very important here in our next statement here of how we tie all of this together. The rate law of an elementary step is determined by its molecularity. Now, it's important to remember here that the order is equal to the stoichiometric coefficient. Now, to help tie all of that together, what I have here is our example chart. So in this example chart, what I'm going to do is talk about each of the molecularities and be able to develop the rate law for that particular step. So we'll start out with our first example here. Let's say we have some generic substance A or reactant A, and A by itself is going to decompose and produce these particular products. Well, the molecularity of this particular step would be unimolecular, and the reason that it is unimolecular is because it only involves one reactant. If you look back on the previous page of notes, you'll see that a unimolecular molecularity says, hey, we only have one reactant. Now, the rate law for this elementary step would be as follows. You'd have the rate, which is equal to the rate law constant times the concentration of our reactant raised to the coefficient. Well, we have a coefficient of 1, so we leave it as this. Now let's say that we have A and A and B combined together to form these particular products. Well, because we have two reactants, this would be a bimolecular elementary step, and it would get the rate law of the rate equal to K times the concentration of A raised to the coefficient, which is 1, so we leave it as is, times the coefficient of B raised to the coefficient there, which is also 1. Now let's say we have two of the same molecules. So let's go back to A and A. And these things smack each other and produce these products. And we could have this because we had two reactants. I know they're the same reactant, but because we have two of them, they had to smack each other that enough speed and that proper orientation. Because they did that, this is a bimolecular step. It involves two of the reactants. Now, this, and you don't have to write this down, but this could also be written as 2A produces the products. Okay? So this is the same thing. Okay? Now, if we use this in mind, it makes it a lot easier to write the rate law. So our rate is going to be equal to K times the concentration of our reactant. Well, we only have the reactant A, but we have two of them, so it'd be raised to the second power. Now, this right here is a good chart to reference, but I also included another chart in your notes. And that other chart is exactly what we went over, except for the fact it goes through termolecular steps. Now I'll get into reasons here in just a second of why I didn't include termolecular steps, but this chart outlines what elementary step or how many reactants you have in each elementary steps to what is the rate law of that particular substance. Okay. Now what we're going to transition to is how do we determine the rate determining step if we have multiple steps or multiple elementary reactions. So how we determine what the rate determining step is if we have multiple step mechanism or multiple elementary steps is we have this. One, we have to keep in mind that most reactions occur by mechanisms with more than one elementary steps. And often, one of these steps is much slower than the others. Now, the other key point to keep in mind is that the rate determining step is the slowest step that limits the overall reaction rate. Now, this is known as the rate limiting step of the reaction. Now, this also governs the overall rate law for the entire or overall reaction. Now, we need to be able to put this knowledge together along with that chart that I just showed you to be able to determine if a reaction mechanism is a valid possibility. So number one, the sum of the elementary steps must equal the overall balanced equation. The second thing is, for this class, there is going to be no termolecular steps. It is possible, and quite often does happen, where a reaction has those termolecular steps. Now, the third thing that we have to be aware of is that the rate law predicted by the mechanism must equal the experimentally determined rate law. Again, this step says the rate law predicted by the mechanism must equal the experimentally determined rate law. So let's go ahead, let's do a couple examples where we put these steps right here to the test. Okay, so we have this. Consider the reaction. Nitrogen dioxide combines with carbon monoxide to produce nitrogen monoxide and carbon dioxide. Now, experimentally, the rate law was determined to be rate equals K times the concentration of NO2 squared. So the overall rate order is to that second power. Now, this will always be given to you in these types of problems, and then it's almost like a proof in geometry class where you have to prove that, hey, some scientists said, okay, to get an experimental rate law like we have here, maybe if we have this reaction in step 1 occur in this reaction in step 2, maybe we can determine what is happening. Again, this is a prediction, and we're trying to prove that it can happen. Okay, so the first thing says is, hey, these reactions added together must equal the reaction that's given. So we have to check and make sure that is a valid point first. So we are just going to add these equations together to make sure that they match the equation that we want. So what we're going to do is this. We're going to add them together. Now, this is very similar to Hess's law, if you're familiar with that. But in Hess's law, just like we have here, if there is the substance on the opposite side of different equations, we can cancel them out. So what I mean by this is as follows. NO3 is on the reactant side of this bottom equation, and NO3 is on the product side of the top equation. Because they're on opposite sides of different equations, we can cancel these out. So I'm just going to cancel those out by drawing a light pencil line through them. And then I'm going to look for anything else. Well, I also find NO2. Now, all I have to do, NO2 is on the reactant side of the top equation and on the product side of the bottom equation. So just one of those products or one of those NO2s can cancel out. I look and I find or try to find anything else that can cancel out, and the answer is no. So all I'm going to do is add these two reactions together. So I'm going to end up, when I add them together, I'm going to get NO2 gas plus carbon monoxide gas is going to be producing nitrogen monoxide gas plus carbon dioxide gas. Okay, so we look up here and we say and compare these two reactions. Well, hey, they're the same. So right now, step 1 says, hey, we don't have to worry about this. Now, we have to worry about step 2, which was no termolecular steps. So no 3 substances in each of our steps. And the answer to that is, hey, we only had a maximum of a bimolecular step. Now the third thing is this. The rate law predicted by these steps must equal the experimentally determined rate law. Well, you may be wondering, well, how do I know what is the rate law? Well, remember, the rate law is the slowest step. So the rate law of this proposed mechanism is just going to be this slow step. So I'm just going to cover this up. And remember, the rate law is equal to K times our reactant, which our only reactant is NO2. Now, just like we had from our chart, NO2 and NO2, if you add those together, that would be 2NO2, or a coefficient of 2. So this rate law predicted by the reaction mechanism would be rate equals K times the concentration of NO2 squared. Okay, so now we have to check and make sure that the rate law is equal to what we have experimentally determined. This matches up with that, and so what we can do, what we've just proved, is that this proposed mechanism is a possible way we can write out our steps. So what we end up writing here is that these steps, this is a valid mechanism because we added up together, they equal the same reaction, and the rate laws were equal, which were determined by the rate determining step. Now, I want to talk about the reaction diagram. Okay, so the reaction diagram for this particular reaction, if you remember from the last section, remember we would have the potential energy, and then on the bottom here we would have the reaction progress. And so if we did the reaction diagram for the proposed mechanism, it would look like this. We would start out with our 2 NO2s, and then we would get up to this first hump, and then we would have this dip, and then we would go to the second hump, and we have our products. Now I looked this up, and it is an exothermic reaction, so that's why we have this thing here. And we still have the activation energies. And what I want to add, what I didn't get to telling you about in the first or the last section, is this guy right here. Right here, this middle hump, this is known as an intermediate. So an intermediate. This is a substance that is formed in one step and then consumed in another. Well, let's take a look at NO3. Look how in this reaction here it produces NO3, and then in the next reaction it is used up. So I'm going to box this up, and I'm going to say NO3 is our intermediate. So again, the definition of an intermediate is it's produced in one step and used in the following step. All right, so again, that is an intermediate. It's a substance produced in one step and consumed in the other. Okay, so let's go ahead. Let's try one more example, and I kind of throw a curveball at you, but let's try one more example here with this reaction mechanism business. Okay, so again, we always get given the equation that we're trying to find for, and we get this experimentally determined or derived rate law. And our rate in this case equals K NO2 squared times the concentration of Br2. And here is our proposed mechanism. We have these two steps, And what we want to do first is we want to make sure if we add these reactions together that they equal this reaction up top that we desire. Okay, so again, same rules apply. If you have one substance on the opposite side of another reaction, we can cancel out. So if we look all around here, the things that we can cancel out is NOBr2. Again, it's on one side of the top equation and on the other side of that bottom equation. So we add these together, and so when we add these together, we end up with nitrogen monoxide gas, plus our Br2 gas. And if we look here, we had NO and NO. So there's actually two NOs, something to be aware of there. And then on our product side, the only product that we have is 2NOBr. Okay, so we look closely here, and if we double check, these things along with their coefficients match up. So that's good. And now remember, the same substance, we can put a 2 coefficient or a coefficient that directly correlates with this. So our first step is good. We have these added together to equal what we want. Now we check and we make sure there's no termomolecular steps. There is not. Remember, that's 3 or more substances there. And then we have to figure out the rate law. Okay, so the rate law is determined by the slowest step. So that slow step here, it's written out. The slow step is step number 2. And if we go by this step, we can write the rate law as follows. So the rate is equal to the rate law constant times NOBr2, and that's raised to the first power, times NO. Now we check this out. The rate law up here does not match up the rate law here. So at first glance, this proposed mechanism might not seem like it could be a possibility. But here's this thing, and this is that curveball I was talking about throwing at you. This right here is an equilibrium reaction. So what that means for us is that we could actually have two rate laws equal to each other. So the first rate law, if you see this K1 over this reaction going from left to right, our first rate law would be K1 times NO, which would be raised to the first power, times Br2 equals the inverse of our rate law constant times, in this case here, because we're going from right to left, our reactants would be NOBr2. So now I ask you, or now I want you to think, okay, we got to get rid of NOBr2, and we need to replace it with things that we have in our rate law. So what we're going to do here, we're going to do a little substitution, and we're going to solve for NOBr2. Okay, so how we do this? This K inverse K is attached via multiplication, so we get rid of that via division. Now, anything divided by its inverse is just going to be 1. So this is going to cancel out to be 1. And so we are left with NO times the concentration of Br2 is equal to the concentration of NOBr2. So now we can do a little bit of algebra. We can do some substitution. So if NOBr2 is equal to NOBr2 here, we can substitute this stuff here with this stuff. So what I'm going to do here is I'm going to do exactly that. So I'm going to have the rate equals K, the rate equals K times not NOBR2, but this business down here. So K times NO times BR2 still times this NO. So now we have to think to ourselves, okay, the rate equals K times NO times NO. Well, anything times itself we can raise to that squared power. So the rate equals K times NO squared. And then we have our BR2. So now via substitution, and because we had equilibrium, which, like I said, is kind of a curveball, we can have this particular rate law. Now, the rate laws now match up. Now, the one thing I want to add that I was just looking at the problem is that this is the fast step, and it should have said at equilibrium. Okay? So that's where I was getting that information, that knowledge. I didn't realize it was not there. But that, because it's at equilibrium, we can do this business here. And so now we can verify that the rates do match up. And you can put, yes, this is a valid reaction mechanism. Now, what we can do here is move on a little bit and talk about our catalyst. So I'm just going to give you some brief orientation of what a catalyst is, and we will be done for the section. So, in chemistry here, a catalyst is defined as a substance that changes the rate of a chemical reaction without itself undergoing a permanent chemical change in the process. So there's some certain qualities that we need to talk about that are associated with a catalyst. So the first thing to be aware about a catalyst is that it is included in the rate law. The other thing to be aware of is that it's not consumed by the reaction. And in a mechanism, it is used in one step and regenerated in a later step. Now, it's not included in the overall balanced equation. Now, we should also be aware that there are two types of catalysts. The first type of catalyst is a homogeneous catalyst. And this is a catalyst that is present in the same phase as the reacting molecules. The other type of catalyst is a heterogeneous catalyst. And this catalyst exists in a different phase than the reactants. Now, something to remember here is that a catalyst is going to lower the overall activation energy for a chemical reaction. Now, I'm not going to write this down, but an enzyme are biological catalysts that produce a reaction, or the enzyme catalyzes the reaction on what they call an active site. Now, this active site on this enzyme is called a substrate, and this substrate uses a lock and key model. Now, what happens here with that lock and key model with each and every substrate is that it is specific to making that reaction go faster for each and every biological reaction that has a enzyme. But just know that an enzyme is a biological catalyst that uses that lock and key model. All right, so a lot of stuff happened here in these final sections of our kinetics unit. I hope you have enjoyed this particular episode and learned a lot. And as always, if you haven't already, make sure you subscribe.